Good morning, all of you. Can you hear me?
Morning, ma'am.
Good morning. Happy New Year to all of you. Next, we are going to see lattice enthalpy versus hydration enthalpy. Can you hear me?
Yes, ma'am.
Lattice enthalpy. Lattice enthalpy means in the crystalline lattice as a solid, whether it will form a solid or putting in water will it dissolve. That is hydration therapy. Hydration therapy is the amount of energy released when they get dissolved in water. If it is not getting dissolved in water, suppose barium sulfate. Barium sulfate, you know, last year you learned it as a white precipitate. When barium chloride is added to sodium sulfate, you got white precipitate of barium sulfate, and you see that white precipitate solid. That means it is in the solid format. Its lattice enthalpy is higher. Its lattice enthalpy is higher. Lattice enthalpy is the amount of energy when these ions come and form a solid. So, lattice enthalpy is the amount of energy released. Or definition you can talk in terms of required also. It is the amount of energy required to break one molar bonds into solid format. Or it is the amount of energy released when these Ba2 plus ions and SO4 minus ions come and take the position of the crystal lattice in the solid format. So, lattice enthalpy or hydration enthalpy. Suppose when we put this in water, it got dissolved. Suppose it won't get dissolved. If it gets dissolved, we say its hydration enthalpy is higher. Means for dissolution, it releases lot of energy. For a process to be spontaneous, we know that release of energy is the one of the best criterion. So, hydration enthalpy means on dissolution, on dissolving, how much amount of energy is released? How much amount of energy is released? Lattice enthalpy, how much amount of energy is released when these ions come to take the position of the crystal lattice, solid format? So if hydration enthalpy is higher, it will get dissolved. If lattice enthalpy is higher, it won't get dissolved, it will be in the solid format. So a substance, whether it is solid or in the solution, that depends upon which is more, that will be having, say this is calcium carbonate, this chalk is calcium carbonate. So many Ca2 plus ions and CO3 2 minus ions are uh, joined together, when standing together to form this. So in this case, see if you put this chalk in water, it will not dissolve. You will see that white solid suspension. You see white solid particles in the suspended format. So its hydration enthalpy is less. Its lattice enthalpy is higher. Its lattice enthalpy is higher. That's why it is in the solid format. If hydration enthalpy is higher, even in this moisture, it would have been dissolved. For example, sodium chloride, it gets dissolved easily. It gets magnesium chloride, it gets dissolved easily. So here, magnesium chloride is somewhat covalent also. It is more soluble in covalent solvents. So here you see why the lattice enthalpy is higher. I am writing all. That is beryllium sulfate, beryllium sulfate, magnesium, calcium, strontium, barium, sulfate, 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 sulfate. This is bigger, this is bigger, this is bigger, this is as we come down, the size of these atoms or ions are increasing. With sulfate, all are big. Sulfate around sulfur, 4 oxygens. Around sulfur, 4 oxygens, bigger size. Barium is bigger. Bigger, voting is good. Smaller, voting is good. But one smaller and one bigger. One smaller and one bigger. Bond is not strong. So what happens? So what happens? Here, the bonding is stronger. Bonding is stronger means their lattice enthalpy, they come close to each other and they attract each other. Their bonding is very strong. When bonding is very strong, it will be in a solid format. This will be in a solid format. You put this in water, this in water, this in water, this in water, this in water. This will not be soluble. But beryllium sulfate, see one small and one big. Bonding is not strong. So in this case, lattice enthalpy is higher, hydration enthalpy is lower. But in this case, lattice enthalpy is less and hydration enthalpy is higher. So whether a substance is solid or liquid, that depends upon their lattice enthalpy and hydration enthalpy. If you put in water, uh, whether a substance is soluble in water or not, that depends upon its comparison with the lattice enthalpy and hydration enthalpy. Now, calcium carbonate. Carbonate is again bigger and writing beryllium carbonate. Magnesium carbonate. Calcium carbonate, strontium carbonate, barium carbonate. So here, as we come down, carbonate is bigger, barium topaz is bigger. Between same size, the bonding is very strong. Here, beryllium is smaller, carbonate is bigger. Magnesium, little more bigger than beryllium, carbonate is very big. Calcium and carbonate, somewhat matching. This is that calcium carbonate and the solid format. Strontium carbonate. Calcium carbonate you can say sparingly soluble. Sparingly soluble. Very less soluble. Barium carbonate insoluble. Barium carbonate insoluble. So between bigger size and bigger size, in similar size, same size bonding is very strong. So in that case, lattice enthalpy is high. Now I took bigger one sulfate, bigger one carbonate, bigger one. Now let me take that side, smaller one. Instead of this bigger sulfate and bigger carbonate, let me take one smaller one. That is OH twice, OH twice, OH twice, OH twice. This is OH, OH twice, OH twice. Now, this is smaller, OH is also smaller. So between between similar ones, bonding is strong. So beryllium, this is in the solid format, but this will dissolve because barium is bigger, barium 2 plus is bigger, OH minus is smaller. So between bigger and smaller, the bonding is very weak. When you put in water, it will detach, the bond will be broken, that will get dissolved. So here, BeOH twice lattice enthalpy side. This will not dissolve. Will not dissolve. But here will dissolve. Dissolve. So that's which is higher. So we can say its hydration enthalpy is higher than lattice enthalpy. Its lattice enthalpy is higher than hydration enthalpy. Which is more, which will be releasing more amount of energy, that will be happening. That will be happening. So BaOH twice will dissolve in water. So write English. We will first write barium sulfate. Barium sulfate is insoluble in water. Barium sulfate, BaSO4. The previous one, BaSO4 is insoluble in water. You call it as a sparingly soluble, but it is almost insoluble only. Barium sulfate is insoluble in water. So you have to talk in terms of hydration enthalpy and lattice enthalpy. So like this, its lattice enthalpy is higher than hydration enthalpy. Its lattice enthalpy is higher than hydration enthalpy. Its lattice enthalpy is higher than hydration enthalpy. So next question, BeSO4 is soluble in water. BeSO4 is soluble in water. About its hydration enthalpy is greater than its lattice enthalpy. Its hydration enthalpy its hydration enthalpy is higher than lattice enthalpy. Next question. BeOH2 ice is less soluble in water. BeOH2 ice is less soluble in water, while BaOH2 ice is more soluble in water. Is more soluble in water. Account. So first we are talking about the top one. The lattice enthalpy of top. The lattice enthalpy of BeOH2 ice is greater than that of lattice enthalpy is greater than the hydration enthalpy. While in the case of BaOH2 ice, hydration enthalpy is greater than lattice enthalpy. Hydration enthalpy is greater than lattice enthalpy. So you have to write in terms of hydration enthalpy and lattice enthalpy. Which is more? That will be which is more means which is released. That will be happening. So one of the criteria of spontaneous process is it's the amount of energy released. During a process, if lot of energy is released, means that process will be happening. Okay. Next heading: anomalous behavior of beryllium. Anomalous behavior of Be. Beryllium, magnesium, calcium, strontium, Be. So among these members of this group, beryllium is exceptionally small size. Yours is upper size and shape. So beryllium size is very small. Size is very small. It is coming in second period. No d orbital. The size is very small. So due to this exceptionally small size, its charge upon radius ratio, small size and charge upon radius is in the denominator, that radius is very less, charge all are having plus 2 charge upon radius ratio is very high in the case of beryllium. So what will happen? Its polarizing power will be high. If it makes a covalent bond, means the shared pair of electrons will be pulling towards the center. It can easily polarize other atom. We can easily polarize other atom. If that other atom is bigger, then polarizability of that atom will be higher. So beryllium can easily polarize. Beryllium will be easily polarizing and is distorting that other atom and pull that electron density towards the center. So beryllium compounds are covalent. Rest all are ion. Beryllium compounds are covalent due to its small size. Small size means high charge upon radiation. Charge upon radiation. This is high. This is high. So its polarizing power will be high. its polarizing power will be high. So, due to these things, uh, due to these things, compared to other high ionization enthalpy, absence of d orbitals. So, due to these reasons, beryllium shows anomalous behavior. So, note down, due to small size, reason, due to small size, high I dot E. Others are having low I dot E. High, due to small size and high I dot E, comma, absence of d orbital. Absence of d orbital means it cannot expand its covalency beyond 4. Maximum covalency it can show is 4. Root 2s, 2px, 2py, 2pz. So maximum covalency it can show is 4. Others can expand their covalency. Okay. Uh, then high charge upon radius ratio. High charge upon radius ratio. These are the reasons for this anomalous behavior. Now, what are the anomalous behavior? Number one, beryllium shows coordination number only 4. Coordination number means around beryllium, how many atoms can stand around? It's the nearest neighbors, how many? How many nearest neighbors? That is what is meant by coordination number. So beryllium, being a small one, it cannot hold so many around it. It can hold maximum 4, as it has got only 4 orbitals in the valence shell. That is what is meant by coordination number or covalency. So beryllium shows a coordination number only 4, as it has only 4 orbitals. Only 4 orbitals in the valence shell. 4 orbitals in the valence shell. That is 2s, 2px, 2py, 2pz. These are the 4 valence orbitals. Others can show more than 4. Others can expand their covalency due to the presence of d orbitals. So that others can show 6, the covalency of 6. By making use of d orbitals. By making use of d orbitals. Number 2. Due to its high polarizing power, in bracket you can write high charge upon radius ratio. High charge upon radius ratio. Due to its high polarizing power, it can form covalent compounds. It can form covalent compounds. It can form covalent compounds. Number 3. You know that these are metals. Metallic oxides, when they form oxides, those metallic oxides are basic in nature, right? So metallic oxides are basic in nature. Uh, calcium oxide when dissolved in water, you get calcium hydroxide and alkali. But beryllium oxide is not acid, it's basic. It is not basic, it is amphoteric. Right? Oxide of Be is amphoteric, unlike others. Oxide of Be is amphoteric in nature, unlike others. unlike others. These are the anomalous behavior of beryllium. Now, write one question. Why does the solubility of why does the solubility of alkaline earth metal hydroxides alkaline earth metal hydroxides in water in water increase down the group increase down the group. Answer: as we go down, hydration enthalpy increases. Hydration enthalpy increases. More and more energy will be released on dissolution in water. Hydration enthalpy increases and lattice enthalpy decreases. And lattice enthalpy decreases. And lattice enthalpy decreases. Now, next we are moving to diagonal relationship that will be taken in the next